This is the most famous piece of footage in the history of physics. A bridge twisting itself to pieces. And almost everything you were taught about why it happened is wrong. Not slightly wrong, wrong mechanism, wrong cause, wrong lesson. By the end of this, you'll see the real thing happen in a simulation, and you'll understand it better than the textbook that got it wrong for 50 years. Here's the puzzle I want you to hold on to. On the morning it fell, the wind wasn't gusting. It was a steady gale. There was nothing out there beating like a drum. So where did the energy come from to rip apart thousands of tons of steel and concrete? Hold that question. It's the whole video. First, the story you probably know. The wind, it said, blew in rhythmic gusts. Some versions say swirling vortices, at just the right frequency to match the bridge's own natural rhythm. Like pushing a swing at exactly the right moment, each push adding to the last, the motion grows until it's uncontrollable. That's called resonance. It's real, it's how an opera singer shatters a glass, how a marching army can break a bridge by stepping in time. It's a beautiful idea. It's in textbooks all over the world. And for the Tacoma Narrows Bridge, it's simply not what happened. 3 problems blow the resonance story apart. 1. The wind that day was steady, not pulsing. Resonance needs a rhythmic push. There wasn't one. 2. There were swirls of air peeling off the bridge, but they came about 5 times too fast, around once a second, while the bridge was twisting only about once every 5 seconds. You can't resonate a slow swing by tapping it fast. And 3, the deepest one. In real resonance, the push comes from outside and doesn't care what the bridge does. But here, the force depended entirely on the bridge's own motion. Freeze the bridge, and the force that destroyed it vanishes. That's not something the wind did to the bridge. It's something the bridge did to itself. Let's go back. The Tacoma Narrows Bridge opened July 1st, 1940, in Washington state, the 3rd longest suspension span in the world. But it was thin. Its deck was a flat, solid ribbon of steel, only about 40 feet wide, and it moved. From day one, it rolled and rippled up and down in the wind so much that workers nicknamed it Galloping Gertie. Drivers said cars ahead of them would disappear into the dips. Engineers watched, a little nervous, but that rolling motion was gentle and self-limiting. It never grew out of control. Then came the morning of November 7th. A steady wind of about 40 miles an hour. The bridge was doing its usual rolling dance. And then, around 10 o'clock, something changed. A cable band at the center slipped, and the whole motion snapped into a completely different shape. The bridge stopped rolling and started to twist. And this twisting was violent. The center of the span held still, while the 2 halves corkscrewed in opposite directions. One edge lifting nearly 30 feet as the other plunged down, the deck tilting as much as 45 degrees. A man named Leonard Coatsworth abandoned his car on the deck and crawled to safety on his hands and knees. The only life lost that day was his dog, Tubby, trapped in the car. Everyone kept asking the same thing: the wind is steady. Why is this getting worse? Here's the real answer, built one piece at a time. Start with the shape. This deck is flat and blunt. Aerodynamically, it's a brick, not a wing. When wind hits a blunt shape, the air can't hug the surface. It rips away at the edge and rolls up into a vortex, a spinning pocket of low pressure. Now tilt the deck just a little. That tilt changes where the air separates and where that spinning pocket sits. And a pocket of low pressure is a suction. So the position of the deck decides where the suction pulls. Read that again. The bridge's own angle controls the force on the bridge. Now the crucial part, timing. Normally, air fights motion. Push something through air and drag slows it down, that's damping, and it drains energy. At low wind speeds, that's exactly what happened here. The air actually calmed the bridge. But as the wind climbed, the timing of that self-made suction shifted. Above a critical speed, for Tacoma, about 40 miles an hour, the suction started arriving at the wrong moment. Instead of fighting the twist, it pushed in the same direction the deck was already twisting. The air stopped removing energy and started adding it. Engineers call this negative damping. And it's the villain of our story. Once the air is feeding energy and instead of draining it out, you get a runaway loop. The deck twists. That twist reshapes the air. The reshaped air pushes the twist further, which reshapes the air more. Each swing bigger than the last, not adding up steadily like resonance, but multiplying, exploding upward. This is the same family of instability that makes a flag flap in a breeze and a reed buzz in a clarinet. Small, harmless examples of a body feeding its own motion from a steady flow. Tacoma was that exact effect, scaled up to thousands of tons. And this is where the mystery pays off. This is a real fluid simulation of that deck section, in a steady wind at the critical speed. Watch what happens. The air separates at the leading edge. A vortex forms and sweeps across the deck. But notice, it's locked to the deck's twisting, not to any outside clock. And here's the proof. Watch the aerodynamic force. It leads the twist. Every single cycle, it does positive work. It pushes energy in. Now the two receipts. On the left, the net damping of the system as we crank up wind speed. It crosses zero right at the critical wind speed of that day. Past that line, damping is negative. And on the right, the amplitude over time. A clean exponential explosion. There it is. There's the energy you were looking for. It never came from the wind's rhythm. It came from the bridge's own motion, amplified by a steady flow. Not resonance. Self-excited flutter. This wasn't just a spectacular failure. It rewrote how we build. Engineers realized you can't just make a bridge strong, you have to make it aerodynamically stable, so it can never feed its own motion. That's why modern suspension decks aren't flat ribbons anymore. They're shaped like wings, with gaps and slots to let air pass cleanly through, and they're tested as scale models in wind tunnels before a single cable is spun, measuring exactly when that damping would flip negative, and making sure the wind never gets there. Every great bridge you've driven across since 1940 was designed by people who learned this lesson from Gertie. So the next time you hear that the Tacoma Narrows Bridge died of resonance, of the wind matching its natural frequency, you'll know the real story. The wind never kept a beat. The bridge wrote its own music, from a steady breeze, and played it back to itself louder and louder until it came apart. It didn't get shaken to death. It shook itself. And now you understand it better than the textbook ever did.